All right, so we're into the Zeiss portal. So I found this to be a little bit, what's the opposite of intuitive? Clunky? I found this to be a little clunky when I tried to get on here the first time. So the first place you want to go is Academy Metrology. Then you want to come down here to e-learnings and click See Online Trainings. Now, the interface that we're about to look at may look a little bit different to you than it does to me because I've already signed up for some additional e-learnings. Okay, so here are the additional courses that I've signed up for. You may or may not see these. Do you see those?
Yes, I
You do? Okay. The one that we actually want should be called Zeiss Academic Program Curriculum. It's a picture of two guys standing at a CMM inspecting a diameter on a housing. And so click on that and you should see this.
Okay.
Perfect. Yeah, so you want to go see online trainings. Resetting password.
I tried the email,
Huh. Is it in your spam folder maybe? Trash folder. Very strange. So you're getting an error?
Yeah.
Very strange. All right, we'll have to deal with that later. Were you able to log in?
Yeah, I'm
Okay, great. And how about you? Is it working? I guess I'm not the only one that had the issue with password, huh? What's that password? I did the auto password generator and it was very strange. And I said, oh, that'll work. And it works fine. I just can't remember it. All right, so go down to, scroll down a little bit. Go to see online trainings. And the website's a bit slow. Were you able to get on?
Yeah.
All right, perfect. All right, so it looks like most people are able to get on. You should see this. It says basic concepts at the top. You can expand tactile coordinate metrology basics or basic concepts. Right, you can expand each one of these, and I guess we'll go right into fundamentals of manufacturing metrology first. Now, I didn't assign any of these modules for this week because, frankly, I wasn't sure. I wasn't getting a lot of response from the admins over at Zeiss until today. So we're going to kind of front load this course, but I'm going to honor what I had on Blackboard at the beginning of this week. All you have to do this week is install Calypso and then balloon a couple of drawings. We're going to go over that right now. However, for the next probably 3-4 weeks, you're going to find that the content is very, you're all set? So what was it, just a time thing?
No, I just had to go.
Log out and log back in?
No, I just had to go to my learning. I still got these pop-ups up here, it's just the rest of the page is an error.
Strange. Okay, but you're on now. That's good. All right. So yeah, the next couple of weeks will be content heavy on Curio Z, and the reason I want to structure it like that is because, well, this is just like CNC 1, where you kind of need to know everything before you can do anything. You know, these machines are going to run automatically, so you need to know how to turn them on and power them up, and then do a basic alignment before you can start writing programs. So if you think it's a lot of content, I get that, and I kind of apologize in advance. However, it will lighten up significantly as we progress through the semester. So I am going to jump into this course right here, and we'll take a look at what sort of things are in here. All right, so I found that these estimates are pretty spot on. If anything, you can go through faster than what it says. So this first one is going to take 30 minutes. You just hit start, it'll walk you through how to use the course, and you can go through at your own speed, or I believe it actually reads to you if you have your sound on. So that's all pretty self-explanatory. One thing I would recommend, if you see any things that look like buttons on the screen, click them, because a lot of times they hide, it's just like the CNC tutorials, they hide a lot of content inside of one button. So if you already know what that button is and what it does, don't click on it. If you're curious, click on it, and in this case, there's just one little flyout. There are other cases as you get deeper into the semester where instead of that being a flyout, there are entire menus upon menus upon menus within that one button, and you'll miss a lot of the learning if you don't click on it. So I kind of like the way they did this. I kind of don't like it. I like it because you have to pay attention, and I don't like it because it's really easy for you to miss something that's important if you are just breezing through it. All right, so it's interactive. You know, they got videos in there and all that other stuff. Okay, here it says click to replay the graphic. Okay, so once it's done, you just click on it again, and it'll replay that grid. All right, but what I'm really looking for here is at the end of each module.
Welcome to the Zeiss Academy for Metrology. In this module, we will be covering fundamentals of manufacturing metrology.
Yeah, so it'll read to you like that. All right, so there are some examples of things you need to click through, and here we go. So there's an embedded quiz right inside of this module. So the way that I'm going to grade you on these modules, you'll go through, try to pick all the correct answers, and at the end, it'll give you a summary of how you did. You'll take a snip of the summary, and you'll send it to me. Here's the real reason I wanted to show this to you. Yes, this is all pretty self-explanatory, other than how to get into it to begin with. But it's a little bit hokey as you're finishing up quizzes. Like, I had questions where I answered them wrong, and I'm like, okay, let me go back and resubmit my answer. It wouldn't let me resubmit it. So you might end up with some things like that. So what I recommend you do is just use your snipping tool. And for each question, grab a quick snip of it before you do anything with it. And let's see, metrology is defined as the study of measurement and is an important field under a larger scope of manufacturing. I'm guessing true. What do you think? Yeah. And then it'll give you your answer right after that. You click again and it'll move on to the next slide, et cetera, et cetera. Well, to capture all these pictures in case you accidentally do the wrong thing and won't let you get back, I like to just paste them all into a PowerPoint file. So that way, if you're having any issues with it, hey, I can't get back in, I can't see my results, so I can't submit this to Blackboard like you said I have to, I can always just say, hey, can you just send me the PowerPoint of whatever your answers were on the way through, and I'll give you credit by doing it that way. Okay, so I think it's wise if you just take the snip before you hit OK. Let's go through and do this one together, and it should be fast enough. Right, that snipping tool is real nice because then you can just come in PowerPoint and just paste them. You know? All right, so due to the increasing demands of modern metrology, older methods of inspecting parts are being replaced by newer options. The CMM is one of these modern inspection tools. What do you think, true or false?
True.
These are all pretty easy for the most part. Coordinate systems are critical to the theory and operation of a CMM. What do you think?
Well,
Got a wise guy over there? Obviously, that's true. All right, and this is the sort of thing that gets a little bit tricky. I was trying to pull some of these over, and it's like you pull it over here, and sometimes it won't snap back to the correct spot. So while I do really like this as a learning resource, you can expect some hokiness there. Let's see, define the Cartesian coordinate system location, drag and drop the blue numbers to properly fill in the point location. Okay, well this is going to be x50, y25, z30. So x50, y25, z30. Grab that snip of that, just as cheap insurance there. Okay. And blah, 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 blah. Let's take a look at our table of contents here. That's these little 3 lines. You notice right now we're only about a third of the way through. When you get to the end, there will be a review section. And if you click on review, that is where the final quiz for the module is. You can see the answers that I've given here already. And this is actually a perfect example of how this might be a little hokey. You notice how I can click on this and I can click check to move to the next slide, and it won't let me get to the next slide. Sure, I could call Zeiss and have them reset it. If I had just taken snips of this as I was going through, then it gives you cheap insurance. You just send it to me and I can give you full credit for the assignment. Unfortunately, I don't have a great way of monitoring what you're doing in this database. Zeiss didn't set it up for that to begin with. I just talked to the rep on the phone, like I said. She said they're beta testing that right now. Well, it's not going to be done by the time we would use it this semester. So unfortunately, that snipping tool is the best way around this. So this is partially an apology in advance for how hokey that part of the learning platform is, but there's a lot of great information in here. So I picked an example that was just your intro course, so there's nothing too special going on there. But as we get a little bit deeper into here, one of the most important concepts is base alignments. So base alignment is how the CMM finds the machine, or finds the part within the machine's volume. And there are a lot of abstract concepts here where I could try to explain it to you by drawing it on the board, but first of all, my drawings aren't that good. That's why I'm an instructor, not an artist. And second of all, it's just so much easier to be looking at a CAD model. So this software does a great job of showing you some of these things. Like here, you can, let's see, 3 translational. So you can click on that, and you actually see it animate on the screen, as opposed to the way I used to do this in the other CMM class when I'm talking about the different axes. I'm sitting there with my fingers like this, and that's just not as good, right? So it is a great resource. It is a little hokey. You will have to put some time into it. If you want to cheat yourself in your own learning, you can go through it quicker than these introduction slides say. Right? This one says 120 minutes. It did take me roughly 120 minutes to do that. If you want to go through faster and you don't care about your education, go ahead, blow through it faster. Just take snips of your questions as you go through, and I will be none the wiser. But you know when I will figure out whether you've been doing the work or not? When you're sitting at the machine. And trust me, I'm petty. I am not above asking you, could have sworn I saw that in the online resources. Can you tell me what slide that was on? And then I'll walk away. I won't give you the answer as long as it's not going to break the machine. If you continually don't do the assignments and you're doing things that I consider to be dangerous on the machine, you simply won't run the machines. All right, machine's $250,000. The probe head is $15,000 of that. It's really easy to break a probe head. This is our insurance policy, so you got to do the work. All right, so that's that. That is Curio Z. So you'll see a whole bunch of Curio Z modules coming down the pipeline over the next couple weeks, but keep in mind there aren't that many modules in the training platform to begin with. There are only, okay, so I just got the same error. I think there are only 27 modules, and I'm only going to require you to do about 18 of them, and the rest are going to be considered extra credit. So that's going to be your quote-unquote reading for this class. All right, so we did Calypso install, Curio Z access, and an overview. Now we're going to talk about how to balloon a print, and soon enough, I will stop talking, and we'll actually apply what we're learning here. I saw your eyes perk up when I said I'll stop talking. All right, so how to balloon a print. We'll jump into the lab folder, we'll jump into the lab folder and then air motor production mode. And the only thing you'll be able to see right now is V1, simple, low precision. So this is the same production simulation that we did last week, although last week I gave you a finished blueprint, and the finished blueprint didn't match what was actually being output by the dimension report. Since then, I've updated all of these. We have updated prints that are available for you to print out and balloon up. So what do I mean by balloon? I mean we're going to open up the blueprint and systematically check every single dimension that's on it. Oh, that's so much better than the other ones. All right, so when we balloon a print, we want to go systematically and assign a number to every single dimension. The easiest way to do this is to look at the zones on the print. So notice that we have a column for zone 4, 3, 2, and 1. And then for rows, we have B and A. So if I'm looking at zone B4, that is right there. Everything in here is zone B4. A4 would be anything in here. B3 would be anything in here, so on and so forth. So basically, I'm going to start systematically, go top to bottom, left to right, just like you would if you're reading something. And if I hit a dimension, I'm going to put a number on it. So boom, that's the first one I hit. I'll put a number 1 and I'll circle it. The next one I hit within this zone is right here. And you might think that this would be the next one I hit because the leader lines are within this zone. I do it with the actual nominal value. The nominal value is inside the zone even a little bit. As you're going systematically, it gets a balloon number. So I'm continuing down top to bottom, left to right. When I get to the bottom, I start over in our next column. So that was balloon 1 and 2. This must be balloon 3. Technically, the through condition of a hole, or whatever the depth of the hole is, would be a separate balloon number because you want to make sure that's correct as well. And I think you get the idea already. We're just systematically labeling every single dimension. Now, I don't expect yours to be exactly the same as mine, but they should follow some sort of order. You wouldn't want balloon 1, 2, 3, 4, 5, 6. You don't want them jumping all around because then it's really hard to follow later. So that's it. This is intentionally a very, very simple assignment. I'm just trying to get you used to working systematically. So that right there is the answer to your homework, or part of the homework for this week. And you say, but Tom, there must be more. And I say, but wait, there's more. Does anybody remember that from back when we used to have infomercials?
Billy Mays.
Billy Mays?
Yeah.
R.I.P.
Excuse me, Tom.
Yeah.
So, for example, on blueprint number 4, that would be that measurement because it's a through hole that
Yep.
we consider a, or anytime I can get counter state, that would be a measurement.
Yep, so if you have a hole, you actually have a couple of things that could be going on with that hole. Maybe it's a counterbore hole. If it is a counterbore hole, you have the diameter of the through hole, the depth of the through hole, the diameter of the counterbore, and the depth of the counterbore, and you want to be able to itemize them in an Excel sheet separately.
So through hole would be just the whole, will be the depth of the piece itself, right? That would
That's
be the-
correct. So for a through hole, you actually can't check that very well on a CMM, and that segues very nicely into the next point, which is you're not just going to inspect these parts in the CMM, because there are some things that, frankly, the CMM is really not well equipped for. It's not the right tool for the job. Perfect example of that would be through condition of a hole. So how do you check if a hole goes through? You grab the best fit pin, it better go all the way through. Now a lot of people will say you just look at it, you can tell if it goes through. Yeah, but I've also had instances too where I'm drilling a hole in a part and I put a drill in there that does not have, I put a drill in the CNC machine that does not have the same angle that I intended, right? Maybe I'm intending that I have a pretty shallow angle because I'm cutting a hard material and I want my drill to come through like that. But in reality, the tool that I put in the machine had a different angle on it. Maybe it was reground, maybe it was just a different manufacturer. So the blue shows what actually happened and the black shows what should have happened. Well, the problem is when you have a misalignment like this, you didn't actually go all the way through. However, when the human picks this up and looks at it, they say, I can see through that, that does actually go all the way through. I don't care what it looks like, I want to make sure it functions. So that's why we check the through condition. The other thing too, it allows us to be more systematic. We don't have to make exceptions like, yeah, we're going to check the depth and diameter of every feature unless it's a through feature and then we don't check the depth. No, that's too much thinking. We're going to check the depth and diameter of every single feature and then we don't have to worry about exceptions. So that's why we would want to check that through condition separately. Does
So
that
in-
answer the question?
Yeah, so that you gotta put a balloon in each feature,
Yep.
and the dimension of that feature, that will be another separate balloon.
Why don't we, I'm not really understanding the question, so let's just continue,
all right.
and I think maybe the questions will kind of answer themselves. All right, so that is that. Let's open up our CMM FAI template. So if we click on that, it'll automatically download. This is an Excel file. So you will need Excel to be able to do this on your home computer. If you have a really hard time getting Excel, I suppose I can make you a PDF form that would do the same thing. Is show of hands, anybody concerned with their ability to access Microsoft Excel? I would also accept, I mean, I've gotten that as an excuse before. It's like, you know, the day the homework is due, oh yeah, I couldn't do it, I don't have Excel. It's like, okay, well, where were you last week when the assignment was posted on Blackboard? Why didn't you tell me that? To remove excuses, I suppose you could just open this up in Google Sheets if you really had an issue. You could also, at school, just hit File, Print, and then fill this out longhand. So this is just a grid where we're going to systematically verify that we checked everything. So we have line number. This is so that I can tell you, hey everyone, look at line number 10. And the line number may not necessarily correlate with the balloon number, as you'll see. Why would it not correlate? Well, maybe we're using two different gauges to check the same thing. Why would we do that? Well, maybe the gauge itself is not so reliable. Right? So the line number just is part of the sheet format. The balloon number is, well, we'll just grab the balloon numbers off the print right here and just put them in right there. So we'll start with balloon number 1. So what zone is balloon number 1 in?
You said it was B4.
Yeah, so looking at these zones up here, that is B4. Balloons number 1 and 2 are both in zone B4. So why do you think we have zones? What's the utility in that?
If you were trying to describe something to me on a print, you could easily point it out, I guess.
Yeah, a lot of times prints are way more complicated than what we're looking at. There are all sorts of dimensions everywhere, and you might have duplicate dimensions, right? You might be trying to tell me about the 1/4-inch hole, and there are multiple 1/4-inch holes of different depths on different surfaces. It's really hard to tell what's what. So the balloon number is a unique identifier, but the zone just gets you to look in the same area really quickly. So our zone in this case is going to be B4. So characteristic. This is the actual dimension itself. So yes, the balloon is a unique identifier. It does get you to look at the right spot, but the characteristic itself is 780 thousandths, 0.78. So you're just going to write whatever the characteristic is. In this case, 0.78.
You said you balloon according to like the nominal value. So like if there's like a dimension with a number in that zone, that's how you balloon it, not like necessarily what it's measuring, right?
Yeah, if there's any part of the dimension in that zone,
Yeah.
the actual dimension text, I'll throw it in the same.
Okay.
But if you're a little bit off from whatever I got,
Yeah.
as long as it's following a system, I'm
Okay.
okay with that.
All right.
I just try to make it as precise as I can, so that way
It makes sense.
I don't have 3 different ones in the class.
Okay.
All right, so the CMM result is simple. When you run it on the CMM, it's going to give you a result in the dimension report. All you have to do is fill it out in there. For right now, for your homework, obviously you can't fill that out because you don't know what it is yet. For manual gauge, I just want you to say what type of gauge are you going to measure this with. Now, you have to pay attention to the level of precision of the tolerance. This tolerance is 0.78. What's the plus or minus on that? 0.78. So the plus or minus, the tolerance on this is actually implied. And it's implied by the blueprint down here in the title block. So by virtue of this being a 2-place decimal, it is 0.78, which is .xx. We look down here in the title block, all your default break edges and tolerances are down here. So .xx means plus or minus 10 thousandths. Okay. Well, if we had a dimension that was 785 thousandths, first of all, that's a 3-place decimal. What is our tolerance if that's the case?
5,000.
Now you have plus or minus 5,000. So very different implication here. Or even if that was 780, right? Technically, that equates to exactly the same thing as that mathematically, but this one implies more precision. It doesn't even really imply it. It straight up states it right here. Okay, let's say we had this. Okay, if you have the dimension stated next to it explicitly, that's just saying we're not using defaults. We need something other than defaults. It would get very cumbersome if we had to do this for every single one. If we had to state +5, -5, they'd be all over the place. They take up too much room. So you have to know that those default values are right here in the title block. So bearing in mind that we do have this case right here, this 0.78, a machinist would still say that is 780 thousandths. But when you look at the print, you say, yeah, 2-place decimal, I got plus or minus 10. So our high limit 790, our low limit 770. what type of gauge do you think we could use to do a manual verification, right? If the CMM gives us wacky results, which they will from time to time, what gauge are we going to use to verify? I mean, I suppose we could use a height gauge with a dial indicator. That would pretty much tell us where something is within 5/10. Do we really want to take out that precise of a gauge if we have plus or minus 10 thousandths? Or maybe you have calipers sitting right next to you, and that's going to be a lot quicker and easier because you just pick up the calipers and measure it. If you need to measure this on a height gauge because it's a high precision tolerance, well, then you have to go over to the surface plate, you have to have the height gauge, you got to situate the part like that, you got to have a best fit pin. Do you really want to do all that? No, that's the cost of precision. No, you do not want to do anything more precise than you have to, because it'll just end up taking you longer. Keep in mind, you're going to iterate this. You're going to do this hundreds or thousands of times. Right? Don't make it take any longer than it has to. Save your attention and your time for when you need it. So, what gauge are we going to use to verify this? What do you think? Height gauge, micrometers, calipers will be good.
Caliper.
So what's the rule of thumb for calipers? What's the limit on the sensitivity or precision of calipers? What's that?
Yeah, the 10th.
Calipers, I would say plus or minus 5 thou. I'm
Plus
very
minus
confident
5.
that I'm accurate within 10 thousandths total tolerance. In fact, to be fair, I probably trust my reading with calipers to about 3 thousandths total, maybe 5 thousandths total. But if you say calipers are good to plus or minus 5, you're well within that limit, right? So we got plus or minus 10. Yeah, calipers are fine. That's 20 thousandths total tolerance. We'll say calipers. And then your manual result, well, for your homework for this week, you didn't actually measure it on the CMM. You didn't actually measure it manually, so you'll leave those blank. But you fill everything else out. So this is a really simple idea. We're just going to do this for the rest of this sheet real quick. And for these first couple assignments, they're all going to be simple answers. You know, this is intentionally a low precision part. So for the most part, we're going to be checking everything with calipers. Later on in the semester, we're going to repeat this production exercise, but with a higher level of precision. And then we're going to use different gauges to verify whatever the CMM said. We'll also have a slightly different approach to measuring the parts on the CMM. All right, so how about balloon number 2? Let's fill this out quickly. Balloon number 2. Balloon number 2, yep, it's
B2, it's B4.
balloon number 2. It's in B4 as well.
2 and 2.03.
2-inch, 30 thou. Yep. It is a 2-place decimal, so we got plus or minus 10. What would we use to check that? Calipers as well. All right, balloon number 3. Diameter 380. What zone is it in? B3. Characteristic is diameter 380. That is plus or minus 10 as well. What do we use to check that? You could use a pin as well. Either way, it's good. All right, so with this through condition, characteristic number 4, that is also in zone B3. Characteristic is through. What gauge would you use? Really, you should use a pin for that. You could say visual as well. You could run your fingernail over it. You'll feel if there's a little drill point in there. The right way to do it is gauge pins. I just write pins for that. And pretty much the rest of this is going to be the same. Now, this print doesn't have any examples of higher precision tolerances, but some of the other prints do. So let's go bounce over and look at one of those quick, and then we're done with this lecture, and we'll start running the machines. What do you think? Pretty straightforward? Not asking too much? For this week, I'm going to ask you to just balloon 4 of these different parts. There are going to be more than 4 of these parts in this folder, but for right now, we'll just do 4 of them. So that way, when you get over here, you already know how you're going to verify what the CMM says. You're going to have a format that you can just type your results into. All right, so one that's going to be a little bit more precise here will be this piston. So what do you think for balloons? only have 3 balloons on this one. All right, so B4 is going to be our first one, right there. Start over at 3, this is going to be number 2, and this will be number 3. And technically that should say 3. It's amazing, I can stare at these prints all day long when I'm making assignments, but it's not until I put them up on the board or I'm reading them to a class on an online video. It's like, how did I miss that? But anyway, how would we check balloon number 1? What gauge would we use? Now let me ask it a different way. Are calipers capable of measuring something that's that shape? Obviously that's a round part, you can tell from the center line and the isometric view here, so that is a round part. So could I put calipers on it? Sure, I could. But are calipers really going to get me within plus nothing, minus 5/10? You get a total tolerance of 5/10. Now calipers are good to plus or minus 5. So what gauge would we use to manually verify that?
Micrometer?
Micrometer. OD micrometer would be just fine. They go out to tenths. All right, how about balloon number 2? What would we check that with? You got plus or minus 10? Yeah, you can check that with dial calipers. You don't even need to walk over and grab a gauge pin. Just calipers, throw them on there real quick. Measure this diameter real quick. Add the radius to whatever distance you get from here to here. And you're off and running. So that's a lot faster than trying to do that with a height gauge and having to grab the right size pin and all that jazz. All right, how about tolerance number 3? What gauge would we use to check that? Pins? Can we just use regular pins though? Because a micrometer went out to tenths of a thousandth of an inch. And that's built right into the gauge. That was just nice and convenient. But can you really use gauge pins that are incremented in 1,000th of an inch if your total tolerance is 5/10, 0.0005? No. I would put this in your notes. What's the rule of thumb for selecting a gauge given a tolerance? Anybody know? Probably went over this in metrology. It's the 10-to-1 rule. Your gauge should always be 10 times more precise than whatever your total tolerance is. So in this case, our total tolerance is 5/10. So in theory, our gauge would have a resolution or a sensitivity of 50 millionths. Now, if you want to know how to write 50 millionths, that's 50 millionths. So that was our total tolerance. That's what we really should have for our gauge sensitivity. Now, do we have any gauges that are that sensitive in the shop? No. The only gauge that's that sensitive is a CMM. That's it. But the whole point of this is, yeah, we're in a CMM class, but what about when the CMM gives you bad data? How do you reconcile that? How do you make sure that that's actually telling you what you think it is? You've got to verify it manually. So the only manual gauge that we have that'll come even close to this are called 10th pins. 10th pins. Now, the brand name on 10th pins would be Deltronics. So just like if you want a facial tissue to blow your nose on, you would probably call that a Kleenex, right? If you want a 10th pin, you'll probably call it a Deltronics pin. So that is a really important concept, the 10-to-1 rule. Let's go to MSC. That's a standard industrial supplier in the machining industry. And look at that, Grainger must be paying for this. The top result there when you type in MSC. That's pretty aggressive, if you ask me. So I'm just going to type in gauge pins, and your generic gauge pins are incremented in thousandth of an inch. All right, so let's go grab a plug and gauge pin set. And let's see, we have 61 thousandths to 250 thousandths. So that's 190 pieces cost $127, and that is value collection, which is a polite way of saying knockoff brand. So what if we sorted by price high to low? I mean, these things are pretty expensive.
Holy shit.
Yeah, $6,800. Well, that's for 1,265 pieces. But still, I mean, if you divide 6,816 by 1,265, you get a lot of money per pin. Well, those are calibrated to plus or minus 0.005 millimeters. So the tolerance is super tight on those. Obviously, the tighter the tolerance is on something, the more you're going to pay for it. So let's let's just add one word here. Just keep in your mind the regular set of 250 pins, roughly, it's 190. Those ones cost about 150 bucks, rough numbers. So I'll just add Deltronics to the beginning of that. Okay, and there's a set right there. MSC wasn't finding it for me quickly, but look at that, 25 pieces. What's that start at? 25 pieces is $287. For 25 pieces, the other one was 190 pieces for 150 bucks. So, unfortunately with Deltronics pins, you do have to purchase them specific for your application, otherwise you go out of business. So we have sets of Deltronics pins in 1/8 inch, 3/8, and 1/2 inch, and that's all we have. And we have 25 pins above or below the nominal. Right? Each pin is incremented in 1/10 of a thousandth of an inch. So if you have a tolerance that's that tight, if you're lucky enough and it's an outside diameter, go ahead and use a micrometer. It's super, super precise. If it's a hole, well, unfortunately, that micrometer just can't measure inside the hole. So you either need an ID micrometer, which is a separate gauge, a dial bore gauge, or 10th pins. And 10th pins are going to be the simplest to use. So we'll learn more about this as we go. But for right now, those couple of tricks that I just showed you, that's enough to complete your homework. So the assignments that are going to be required, now that you know what to do, will be the top 4 options under the lab folder on Blackboard and the air motor production mode folder on Blackboard. And those top 4 are upright, base, crank, and piston. Right, so upright, base, crank, and piston. And I'll add a little bit more description to what you're supposed to do when I post this video online later. So, and if you want to go back and review this, the link will be right there. If for some reason the link's not there, please just send me an email. It's probably like sitting on my computer waiting to be posted.
What does FAI stand for?
FAI stands for First Article Inspection. First Article Inspection. So the idea here is you're doing a first article inspection, meaning when I set up the machine and I'm going to cut 1,000 parts, I don't just cut 1,000 parts. That would be reckless. I cut one part, and then I inspect it myself to the best of my abilities, given the gauges that I have, and then I submit that to the inspection department. And that's where this class comes into play. Now you're taking off your machinist cap. You learn that in semesters 1, 2, and maybe 3, depending on where you are in the program. Now you're putting on your inspector's cap, and the inspector makes many, many less assumptions than the machinist does. The machinist is making a whole bunch of assumptions about things that should be good based on how they know the part was made. The inspector makes almost none of those assumptions, so you have to be a lot more systematic about it. You have to pay a lot more attention to detail as an inspector. But the bottom line is, if the machinist doesn't catch something and they don't submit a part for a first article inspection, you can make 1,000 bad parts. They're 99% good, but that last 1% violates the contract of the blueprint, and they're all scrapped. Go make them again. See you in a week. Right. Do not pass go. Do not collect $100 or however that goes. All right, so any questions on this? So I'm going to segment the video here, and then we're going to head over and get started on our lab, and we're actually going to do some manual alignments, which means you'll be using the joysticks on the machine. Yay! We'll be setting up some fixtures where applicable, and we'll actually run some parts.